Okay, good morning, everyone. Hope you're doing well. Before we dive back into lecture, congratulations, you reached the 10th and final deliverable. Just give you an idea for what you're in store for this week. In this final deliverable, you're going to be incorporating some scaffolding. And as you remember from our discussion a few weeks back, this idea of scaffolding comes from psychology, and it's the idea of helping a learner get started at a task. And as that learner starts to gain competency in the task, as we observe that growing competency, we gradually and incrementally remove the scaffold until they're able to master or perform the task without our help. So you're now moving into the stage with your final project where you're thinking carefully about how to help the user learn and be able to sign ASL digits on their own. So you're going to be implementing 3 scaffolds this week, and as you'll see, deliverable 10 is only a page long because most of the ideas are going to be up to you this week rather than me. And the attendance sheet is currently in view mode. Thank you very much. Let me fix that for a moment. So you're implementing 3 different kinds of scaffold this week, and the way in which you implement those scaffolds are up to you. So each one is up to you. You're going to be figuring out how to apply it, and then gradually, and then writing up a 1 or 2 sentence description of it that you're going to be submitting along with your video that demonstrates that scaffold in effect, and it's also going to demonstrate the gradual removal of that scaffold as the user signals more competency. Okay, so what are the 3 scaffolds? The first one is going to challenge the user to sign an increasing number of digits as their performance improves. So at the beginning, you'll show just the 2 digits or 1 or 2 digits over and over again. But as they start to sign it correctly, you need to be able to detect that. And then you might fold in a 3rd digit. They practice with the 3. Once they signal competency with all 3, you add a 4th and so on. The second scaffold will increasingly challenge the user to remember the gesture associated with the digit as they improve. So you're going to flash up the image and the digit itself, and then over time, as they get better and better at signing the digit, you're going to show only the digit and not the image of what they should be signing. So they need to memorize the gesture associated with each digit. And the third and final scaffold will increasingly challenge the user to sign that gesture faster as they improve. So once they see the digit 4, we want them to be able to sign that digit as quickly as possible. Okay, so that's deliverable 10, which as usual will be due next Monday, and the following Tuesday, next Tuesday, we'll talk about the interim reports and the final project, which you'll be working on for the last 2 weeks of class. Before the final exam, which for us there is no final exam. You're going to be giving a 2-minute and 30-second oral presentation summarizing your final project. So we have 60 students in the class. We have a little less than 3 hours for our time together. And so you'll be presenting your work orally. I apologize for the time. I realize it's exceedingly early in the morning. I don't set the time for the exams, but we'll all meet very early on Tuesday, December 8th, and we'll be able to sit back and learn about all the various ways that you've thought up for teaching your users ASL. Any questions about that? All good? Okay. So back to our theme on looking outward. We're going to finish sort of the first part of this theme this morning with the Human Speechome project. And in lectures 14 through 19, we've been looking at a large number of applications, different kinds of technologies, and just sort of surveying all the different ways in which we as a society are gradually stitching technology into the world, where that technology can directly sense what's going on out in the world. We've looked at lots of wearable technologies. In the second half of this looking outward, in lectures 22 through 23, we're going to be looking at technologies that are embedded out in the world that can directly sense the world, but they can also act directly on the world. They can push against the world, and because they have sensors, they can observe how the world pushes back. And that technology, of course, is robotics. So we're going to introduce this concept of robots today, and we're going to come at robots from an HCI perspective. We're going to view robots as a technology that takes as input from the world, cogitates on it, and produces output back on the world. And we'll talk about the nature of that interaction in more detail in lecture 21. Then we'll look at robots that interact with people. And finally, we'll end with robots that interact with other people, so robot swarms. Okay, so that's where we're headed. But before we get there, back to the Human Speechome Project, which just as a reminder is this interesting application of ubiquitous computing inside the home of a researcher who's going to use this technology to study his young child and how this particular young child acquires language. And this is clearly a very different way at coming at the problem of understanding how young children acquire language, because it is not being done in a laboratory setting. They are going to passively observe their child's first few months, month 9 through month 24, which we'll talk about later. And as Deb Roy mentioned in his TED Talk here, the data set that was produced by this was and still is the world's largest family photo album or home album. Okay, we got halfway through this TED Talk last time, and we ended by listening to just an audio transcript of every time Professor Roy's child said the child's version of the word water, which was gaga, and eventually the adult form of the word. And these were short audio clips that were taken from different rooms in the house at different times. You might have heard in a few of the short clips, you could hear running water in the background, so the child was either in the kitchen or the bathroom.
So he didn't just learn water. Over the course of the 24 months, the first 2 years that we really focused on, this is a map of every word he learned in chronological order. And because we have full transcripts, we've identified each of the 503 words that he learned to produce by his second birthday. He was an early talker. And so we started to analyze why. Why were certain words born before others? This is one of the first results that came out of our study a little over a year ago that really surprised us. The way to interpret this apparently simple graph is on the vertical is an indication of how complex caregiver utterances are based on the length of utterances. And the vertical axis is time. And all of the data we aligned based on the following idea. Every time my son would learn a word, we would trace back and look at all of the language he heard that contained that word. And we would plot the relative length of the utterances. And what we found was this curious phenomena that caregiver speech would systematically dip to a minimum, making language as simple as possible, and then slowly ascend back up in complexity. And the amazing thing was that that bounce, that dip, lined up almost precisely with when each word was born, word after word, systematically. So it appears that all 3 primary caregivers, myself, my wife, and our nanny, were systematically, and I would think subconsciously, restructuring our language to meet him at the moment of the birth of a word and bring him gently into more complex language. And the implications of this, there are many, but one I just want to point out is that there must be amazing feedback loops. It's not, of course, my son is learning from his linguistic environment, but the environment is learning from him. That environment, people, are in these tight feedback loops and creating a kind of scaffolding that has not been noticed until now. But that's looking at the speech context. What about the visual context? We're now looking at, think of this as a dollhouse cutaway of our house. We've taken those circular fisheye lens cameras and we've done some optical correction, and then we can bring it into 3-dimensional life. So welcome to my home. This is a moment, one moment captured across multiple cameras. The reason we did this is to create the ultimate memory machine, where you can go back and interactively fly around and then breathe video life into this system. What I'm going to do is give you an accelerated view of 30 minutes, again, of just life in the living room. That's me and my son on the floor. And there's video analytics that are tracking our movements. My son is leaving red ink, I'm leaving green ink. We're now on the couch looking out through the window at cars passing by, and finally my son playing in a walking toy by himself. Now we freeze the action, 30 minutes. We turn time into the vertical axis, and we open up for a view of these interaction traces we've just left behind. And we see these amazing structures. These little knots of 2 colors of thread we call social hotspots. The spiral thread we call a solo hotspot. And we think that these affect the way language is learned. What we'd like to do is start understanding the interaction between these patterns and the language that my son is exposed to see if we can predict how the structure of when words are heard affects when they're learned. So in other words, the relationship between words and what they're about in the world. So here's how we're approaching this. In this video, again, my son is being traced out. He's leaving red ink behind, and there's our nanny by the door.
You want water?
All right. She offers water, and off go the 2 worms over to the kitchen to get water. And what we've done is use the word water to tag that moment, that bit of activity. And now we take the power of data and take every time my son ever heard the word water and the context he saw it in, and we use it to penetrate through the video and find every activity trace that co-occurred with the instance of water. And what this data leaves in its wake is a landscape. We call these wordscapes. This is the wordscape for the word water. And you can see most of the action is in the kitchen. That's where those big peaks are over to the left. And just for contrast, we can do this with any word. We can take the word bye, as in goodbye, and we're now zoomed in over the entrance to the house, and we look and we find, as you'd expect, a contrast in the landscape where the word bye occurs much more in a structured way. So we're using these structures to start predicting the order of language acquisition, and that's sort of ongoing work now. In my lab, which we're peering into now at MIT, this is at the Media Lab, this has become my favorite way of videographing just about any space. 3 of the key people in this project, Philip DeCamp, Ronnie Kubat, and Brandon Roy, are pictured here. Philip has been a close collaborator on all the visualizations you're seeing. And Michael Fleischman was another PhD student in my lab who worked with me on this home video analysis. And he made the following observation, that just the way that we're analyzing how language connects to events which provide common ground for language, that same idea we can take out of your home, Deb, and we can apply it to the world of public media. And so our effort took an unexpected turn. Think of mass media as providing common ground. And you have the recipe for taking this idea to a whole new place. We've started analyzing television content.
Okay, I'm going to pause the video there. In the second half of this TED Talk, Professor Roy goes on and describes how he's taken this idea of connecting language with context, who, what, where, when, and how, and applies it to media, which of course is the age that we're now living in with social media analysis. But we're going to focus today on the specific application of using ubiquitous technology to understand the origin of language, at least from the point of view of a new human being. As David mentions, their decade-old 3D visualizations still look pretty good. You can imagine how shocking this was at the time. So this study was carried out in 2009. A lot of ubiquitous technology was still in its infancy at that time. So this was an unprecedented data set. We're going to go back now and have a look at, we're going to dive through this data set in a little more detail and then come back to some of the scientific questions that Deb mentioned during his talk. Okay, first one, as he mentioned, is they instrumented their house with audio and video feeds. So they have 11 overhead cameras that give a fisheye lens view of each room, so they can capture pretty much all the action in the room. 14 microphones as well. They collected data over the following period for their child, 9 to 24 months of age, which is known to be the most intense period of language acquisition. If you've ever been around a child around this age, it's amazing how many new words they absorb and emit during this period. And we'll actually see a visualization of new word acquisition over this period in a moment. During this period, they collected over 4,000 hours of audio and visual, which spanned 444 out of the 488 days that make up this period. So a pretty good coverage they got most of the time. 90,000 hours of video and 140,000 hours of audio, 200 terabytes of data. Again, very impressive for 2009. They got an average of about 10 hours per day. So from the child's point of view, they got most of that child's waking hours. They think they captured about 70 to 80% of the child's waking hours. Of course, they're recording not just the child, but they're recording the 3 other caregivers. So Professor Roy, his wife, and the nanny, they're recording their behavior as well. So given the behavior of these 4 individuals in the home, typically 5 to 6 cameras were active at any given time. Here's a quote from the paper, that's the reading for today, in which Professor Roy distinguishes his approach from the traditional approach, which is theory-laden, meaning that if we want to understand a given phenomenon, which in this case is how children acquire language, we might start our scientific investigation with a theory. In the case of Deb Roy's approach, they're going to start their scientific study not with a theory, but with the data. Why is it better to have a data-driven approach than a theory-driven or theory-laden approach? Well, in a contrast to diary studies, which are necessarily theory-laden, if we go in with theory, since the diarist cannot record everything, he or she must rely on theoretical biases to decide what is noteworthy at the time of observation. So if you have a theory and you're going in to test that theory, you have to decide what observables, what are the things you're going to measure, who, what, where, when, and why. In deciding on what to measure, you're usually being guided by your theory. Observations that you think are going to be irrelevant to the theory or extraneous to the theory, you're not going to measure. So I gave you this example earlier. Imagine that someone has an idea that children learn language through joint attention. The parent looks at an object, says the name of that object. The child looks at the eyes of the parent, infers where the parent is looking. Child changes their gaze, they saccade away from the parent's eyes to the object, and then they say the name of that object. If your theory is that joint attention scaffolds the acquisition of language, then you're probably going to measure direction of gaze and audio about who says what when. But maybe pointing is also an important part of language acquisition, gesture. But in joint attention, we're only focusing on the eyes and what is said, so we may not record who is pointing or what gestures are being made by what individual at what time. We might lose important information if we come at these kinds of questions laden with a theory. Alternatively, in the Human Speechome Project, or the Speechome corpus, the data that makes up the Speechome Project, may be reanalyzed multiple times, guided by different theoretical perspectives. So if we think that joint attention is important, we could dive into the video and try and infer who is looking at what or whom at a given time. If instead our theory says gesture is important, caregivers point at an object and say the name of that object, we might dive back into the data again and now look for hands in the data and what gestures are being made with the hands. The existence of high-resolution video provides opportunities to study the role of various aspects of non-linguistic context. So what are all the things that are going on other than language that may be important for the acquisition of language? Who is looking at what, when, who is pointing at what, and so on. So he mentions joint attention here to routine activities and beyond. Okay. All right, so that's the reason why we're starting with data rather than starting with a theory. What's the data we have on hand? Well, they have raw audio and video data. We are going to try and distill out of this raw data some subset of phenomenon. So we are a little bit guided by theory here. We're assuming that in order to acquire language, language itself matters. We need to listen for words in the audio transcripts. People are probably important. Professor Roy was showing these social hotspots of people, him and his child, that were close together and interacting. He was saying something, the child was saying something. So who is nearby the child when the child says a word or a word is uttered is important. Activities are important, objects are probably important. And then from all of this data, as we dive into this data and look for correlations between when the child says words for the first time, so language acquisition, the birth of new words from the point of view of the child, correlations between those events and these events will support or disprove various theories we could dream up of language acquisition. Okay. So from the audio, we can pull out who was saying what and how. So did the child say something? Where, when were they when they said that word? Did one of the three caregivers say a word, and who and what, where and when did they say it? In order to get from raw audio to this, we need to do some word level speech transcription, speaker identification, who is speaking. We also, as you'll see in this study in a moment, they also focused on prosody. Remember, we talked about prosody before. This is the way in which things are said. How loud was a word spoken? How quietly was a word spoken? What was the pitch of the voice that spoke that word? And various other aspects of the way in which something was said. From the video, they're going to pull out who, what, where, what were they doing, how were they doing it, and with what, so objects as well. So we're looking for people, activities, and objects in the video feed. And here's just sort of a flow chart of how this goes. Once this arc is completed, then we can pose particular theories or particular hypotheses and test it with the data. For example, here's one theory. When was a word spoken by the child for the first time? So within that 9 to 24 month period, did the first time that the child say the word water, was that late? Was it towards the end of the 24 month period? Or was it early? Was it close to that 9 month period? You could, for every new word mentioned by that child during that 9 to 24 month period, so we have the time of onset, how early did they acquire that word? And we could compare it to how often that word appears in the raw audio feed as a whole. So basically, how often was that word spoken in the home before the child said it for the first time? If there is a positive, if there is an inverse correlation, meaning the earlier the word was spoken, the more often that word was heard. If we can find such a correlation, then in the data set, that would support this hypothesis. If there's no correlation between the time that the word is spoken for the first time by the child and the frequency with which that word was spoken in the home, then that lack of correlation would be evidence against this hypothesis. What are some other, given the fact, imagine you had access to this data set, what other hypotheses about language acquisition might you propose, and what aspects of the data set might you go looking for to test it? I'll give you a minute to think about that. If you have an idea, go ahead and type it into chat. So I mentioned joint attention. Maybe that's important. Looking at where the individuals are looking at the time that a word is spoken or detected in the audio stream. You may not be able to remember how you acquired language because you were pretty young when you did. For those of you that have learned a foreign language, and some of you are learning ASL at the moment, what are some of the things that help you learn the words or the gestures in the case of ASL that make up that language? Who do you learn from? What are you looking at? When the person is trying to teach you some language, what are they doing? What are you looking at? Obviously, you might have learned some language from a book, so you might not actually be interacting with a person. The way that adults learn language is probably different from the way children learn language. What are some other aspects? What are some other things you might look for that are going on in the home that you might measure in this data set and look for correlations with words spoken by the child for the first time? What are some events you think might cause a child to say a word for the first time? Television, right? So they have the audio transcripts. I don't know how good those audio transcripts are, if they're able to pick up language in language from the television broadcast. But yeah, that one's probably a big one. You can definitely tell from the video feed where the television is in the home. So this is the pre-2009. This is the pre-YouTube era. So the child is not watching YouTube on a laptop at this point, or at least that's pretty unlikely. We might be able to detect whether the child is sitting in front of the television when they speak a word for the first time. If that happens quite often, that would be evidence that would support Ethan's hypothesis here that TV helps teach children language. If children utter words for the first time very often away from the television, that would be evidence against this hypothesis. Any other ideas? What are some other triggers in the home that help the child to generate language for the first time? Their own basic needs, right? So what is the point of language? At least for children at the beginning, it might be to ask for things. If all you can do is scream and cry, that's fine. It'll usually give you your basic needs. But as you grow a little bit older, past 9 months, there may be specific things you want that it would be easier for you to ask for them by name rather than to throw a temper tantrum. So their own basic needs, that's an interesting one. How could we pull out from the who, what, where, and who is doing what that would tell us that the child is emitting the word because they want something? Any ideas? If the child says a blanket for the first time, let's take Bryce's example of blanket, we can determine where and when in time the child emits the word blanket for the first time. We might be able to then go to the video feed and see a short time later, a minute or two later, does a blanket actually appear? Does the child actually get what they want? Does the object appear shortly after they emit that word? If there is a coexistence between the utterance of the word and the appearance of the object in the word or the object itself, that would be evidence in favor of Bryce's hypothesis. If those co-occurrences are rare, that would be evidence against this hypothesis. Okay, I think you get the idea. Okay, again, this is 2009, automated audio transcription was not very good at the time. So you have 488 days of raw audio. Most of that audio is silent or is non-speech, background sounds. So how do you actually pinpoint the important moments in the audio feed and the video feed, which especially in this case, in the audio feed are words? They did this mainly by creating a whole bunch of interactive tools that allowed the grad students to sift through this vast amount of audio and video, looking for who, what, where, and when to support or disprove various hypotheses. With the audio, they visualized the audio, so they made pictures of the audio feed using what's known as a spectrogram. So a spectrogram works as follows, and I'm sorry for the poor image quality here. You can go have a look at the paper itself to see more details. In a spectrogram, you have time on the horizontal axis here, and on the vertical axis, you have a whole bunch of frequency bands, so low frequency, middle frequency, and high frequency. And in this case, A white pixel at a given point represents there was no amount of that frequency at that point in time. If you take a vertical cut through a spectrogram, you'll get a whole bunch of colored pixels. So colored pixels in this case colored pixels here represent strength of a given frequency. So you can see, for example, in this little screenshot here, there was a burst of sound over this time period. It was initially a low frequency sound rising to a higher pitch and then cutting off. So you can see these squiggles, and you can actually analyze a spectrogram, and there are particular squiggles or particular signatures of words that you can go looking for. So they're basically throwing away all the non sounds, and then eventually the non-verbal sounds, and just focusing in on the words themselves. This audio-visual browser that they made allowed them to look at all of this data sort of over very broad time scales, so they could zoom out to years, zoom into seconds. Not an easy thing to even start to sift through such a massive data set. Automatic speech recognition in 2009 was terrible. Recognition error rates were about 25%, so accuracy was 25%, basically unusable. So they did manual speech recognition. They used spectrograms to sort of zoom in on particular points in time, and they grabbed small periods of time that seemed, from a spectrogram point of view, to be words. They put all of those little snippets into this fast speech transcription application. And then the grad student could click play and listen to that clip, and then they would have to try and indicate whether the transcription actually got it right or not. And so it's not speech, it is speech. So basically the graduate students are trying to clean up the automatic speech recognition, which was pretty terrible. You can imagine this was an incredibly painstaking operation. For 1 hour of possible speech, it took an hour and a half to transcribe into actual words. A lot of manual effort here. Today, this could probably all be automated. Okay. I'm sorry. They typed what was heard. It wasn't necessarily automatic speech recognition. So it was basically 95% grad student effort and a 5% automatic speech recognition here. Okay, so a lot of effort went into this these early stages of distilling raw data down into words. Where were the people, activities, and objects, and so on. Once most of that dirty work was done, then they could move on to the science part. So let's start with a simple question, which is, what is the rate at which this particular child acquired language? So they're going to use this term word birth as a shorthand for when in time was a particular adult form of a word mentioned for the first time. So you heard in the TED Talk last time the child saying gaga, 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 water. So what was the moment at which they issued the word gaga? We can record that here on this vertical the horizontal axis, going from 9 to 24 months. You'll notice in month 9, the child mentioned maybe 3 words, the first 3 words this child ever uttered. The next month, month 10 here, they mentioned no new words. Month 11, a couple of new words. And then in the succeeding months, the child was exponentially uttering new words for the first time. What happened at month 20? Any ideas? So before this study, it was known that new word acquisition grows exponentially in around this period for most children, give or take. And then, of course, it has to tail off at some point, because if you're exponentially acquiring words, there's only so many words in the English language. So the rate of acquisition was known to sort of tail off, but no one really knew what the shape of that tailing off was. At least for this child, there was an extreme tapering off of word acquisition, this extremely dramatic event that occurred around month 20. Any ideas about why there might be this sudden drop? What's going on here? The first thing you might worry about if you don't know this child is that something has happened and they've stopped speaking, or they're speaking much less. As Ethan says, perhaps they found a core lexicon for expression. If you want something, you can obviously ask for it by name. Most children realize pretty quickly if you want other things, the best way to get those things is to issue words in combination. Right? Hot water, cold water, warm blanket, red blanket, favorite toy, and so on. So once you learn grammar, or at least the combinatorial power of language, you don't necessarily need to acquire lots and lots of new words. You need to figure out how to combine those words in combination. And that's probably what's going on around this period here. But this was particularly shocking to most people in linguistics, that there was this rapid a drop-off in the acquisition of new words. So one of the nice things about approaching a scientific question just from the data point of view and trying not to bring in your biases, your hypotheses, is that often the data will present whole new ideas. Right? So this shows not just a drop in rate of increase, which would be a sigmoidal curve, meaning the child is still acquiring more words per month, but there is an actual discontinuous drop here, which might suggest new hypotheses about how children acquire language, or as Ethan mentions here, how they master a core lexicon and move on to grasping the combinatorial power of language. Kind of interesting. Okay. Here's another question and some data that attempts to support that. Does how often a word is heard by the child, how frequently is a word issued uttered in the house, does that predict or correlate with when it will be spoken for the first time by the child? And it seems that the data for this particular child suggests the answer is yes. So again, on the horizontal axis here, we have the age in months of the child. Each dot corresponds to a word spoken by that child for the first time. So here are the two first words ever uttered, adult forms of two words uttered by the child in month 9. The vertical axis represents how often that word was heard in the raw audio stream before this period. So you'll notice that for these 2 points, those words were heard relatively frequently. For this word down here, whatever this word is, this word was only spoken for the first time by the child at month 24, and that word had been heard 0 times. It either wasn't in the audio transcript, or the grad students didn't manage to capture it even once in the raw audio feed. You'll notice that there is a big cloud of this data, so the correlation here, if there is one, isn't immediately clear. And this is not unexpected. This is raw data. Obviously, the audio and video capture of these phenomena, word births or word utterances, is not perfect. A lot of noise in this system. Nonetheless, if you take a straight line and you try and fit that line somewhere in this plot, so that line is as close to all the dots as possible, this is linear regression, you get this red line, which has a negative slope, and the slope of this line is minus 0.3. The negative tells us that there is indeed an anti-correlation here. The later the word is spoken, the further to the right you go in this plot, the less that word was spoken in the house. The further down that point tends to be. Okay, so there is a fit here. There is an anti-correlation, but it's not great. Is there something else going on here that might produce a better correlation? Can we capture a set of phenomenon that better predict when a child will speak a word for the first time? If we could find such a phenomenon, we're getting closer to understanding what causes a child to utter a word for the first time. Turns out that you can. Turns out that word frequency is not the only thing that predicts word birth. So I'm going to unpack this slide for you, but let's start by going down to the bottom of this slide. We just saw in this plot here on the vertical axis, we were looking at F, or frequency, how often a word is heard. Let's take every word that was uttered by the caregivers or uttered by the child, and let's also measure for that word, not just frequency, how often the word was spoken, but its prosody, how that word was spoken on average by the caregivers. In this study, they looked at one particular prosodic feature, which is what's often known sort of tongue-in-cheek as mommy-ease. So this is sort of baby talk. In baby talk, at least in English, we tend to take a word and exaggerate the vowels. Mommy, daddy. So you can actually take, if you capture a word from the audio feed, you can measure the length of the vowel sound, again by using these spectrographs. And the longer the vowel sound, the higher the value of P. We're going to mark it as having more of this prosodic feature, which in this case is more of mommy-ease. Okay, so for all the words, all the points here, we have two numbers associated with it: F and P, how often it was spoken, and how much mommy-ease was used when that word was spoken on average. So far, so good. Given those two features, we can then ask the following scientific question: does how often a word is heard and how it's said in combination predict when it will be spoken? Okay, so how do we test that? Okay, so what we're going to do is we're going to take this figure, which had F on the vertical axis, and imagine I'm going to replot this data, but now on the vertical axis I'm going to plot F plus P. I'm going to add the two numbers, frequency of the word and the amount of mommy-ease, and that sum of those two features will give me the height of this word. We still have the time that word was spoken, so that'll give me a second plot where now I have F plus P on the vertical axis, and I could then fit a new line in that second plot and ask, does that line represent a greater correlation, a stronger correlation, if we're using F and P to predict when a word was spoken, than the relatively weak correlation we got when we used only F. So far, so good? Okay. All right. However, in this hypothetical second plot, we're just mixing F and P, but how much F and how much P should we mix together to look for a stronger correlation? In order to test that, they introduced another variable, alpha, and you can think of an alpha as a slider bar. If alpha is set to 0, we're going to only plot F against A. That's alpha equals 0. If alpha is 1, if we slide alpha all the way to 1, we're going to look at, we're going to mix all of P and none of F together and ask, does just P and A correlate? So in essence, we're creating a new variable, which is going to be alpha times P plus 1 minus alpha F. The more alpha, the more we're mixing in P with F. Make sense? Okay, so if we take this alpha and we slide it slowly from 0 to 1, that's going to produce a whole bunch of these scatter plots with that different admixture of F and P on the vertical axis. And for each of those scatter plots, I can get back a single number, which is the slope of the linearly regressed line. Yeah? Okay, so obviously plotting all of those scatter plots is going to be a lot of visual clutter. Remember our discussion about Edward Tufte when we talked about visual design? We want to maximize the data to ink ratio. If we drew all of those scatter plots for all of those admixtures of F and P, that's a lot of ink. The only thing we're looking for in the data to ink ratio in this case is how does correlation change as alpha changes. So instead of plotting all of those scatter plots, we're going to plot one plot where now on the horizontal axis, we no longer have time, we have all of the different values of alpha. So what is the left hand of this figure represent? Or what does this dot represent at the very left edge of this figure? And obviously, sorry, I forgot to mention on the vertical axis here for that dot, we're plotting the correlation that we obtained for that value of alpha. What does this dot tell us right here? Any ideas? So this dot clearly corresponds to an alpha of 0. If we look down here, an alpha of 0 means we're plotting F against A, or age of the child when he first spoke the word, which is actually this plot here. If you're really paying attention, you'll notice that this point does not seem to correlate to a minus 0.29. So I don't know if this is an error in plotting or maybe just a little bit of noise in the data. But this single point here corresponds to this entire plot here. You'll notice that we get all of these different correlations for different values of alpha, and when we get out to an alpha of 1, we're plotting prosody, the amount of mommy e's in all the words. We're plotting that against how old the child was when the child uttered that word for the first time. And we get a correlation of minus, whatever that is, minus 0.17, a weaker correlation. So mommy ease itself is not very predictive of how early the child will say the word. So if a lot of mommy ease is used, that doesn't necessarily mean that the child will utter that word for the first time earlier. If we go to the bottom of these points around here at alpha 0.2, we have a very strong anti-correlation. What does that mean? So if we work backwards to an alpha of 0.2, what is that telling us about how this child acquired language? How does an alpha of 0.2 translate back into the amount of F and P, and how that amount of F and P predicts how early a word is spoken? What is this point? What is this set of points down here telling us about our hypothesis? It's telling us something pretty specific, actually. So let's start with the alpha of 0.2. How does that translate back into F and P? What's the value of F and P associated with an alpha of 0.2? So an alpha of 0.2 means 0.2P plus 0.8F, meaning there's more F than P in the signal that best predicts word birth. So as Kahn mentions here, this is telling us that frequency has more influence on predicting when the child will utter the word, but not all the influence. So an alpha of 0 is just frequency. So mommy ease has something to do with it. The amount of mommy ease in the words influences how early they're spoken, but it has less of an influence than frequency does. As you can imagine, when we're dealing with humans, the story is always complicated. There's probably going to be no simple explanation of how children acquire language. The way they acquire language is going to be a mixture of lots of things. So as Ethan was mentioning, it's probably a mixture of television, assuming this child was allowed to watch television, their own innate needs for asking things, as Bryce mentioned. As Ethan mentioned, it's probably comes from combinations of words. It's going to be a lot of factors that influence the language acquisition. One of the exciting things about this data set is it allows us to actually get at what combination of phenomena predict language acquisition. Of course, in this data set, it's only going to allow us to test that for a single child. If we were to repeat this process with multiple children, we could ask how those combinations of features. Sorry, I think somebody is unmuted here. Okay, we could ask: is this are these admixtures of features predictive for just this child, or how much do those admixtures differ for different children? Are there very different stories about language acquisition for different children? Okay. Okay. The last set of hypotheses we're going to look at here was actually mentioned by Professor Roy in his talk, which is, do caregivers scaffold the learning of new words? So here we see the appearance of scaffolding again. So this is kind of an interesting idea in language acquisition, which is, of course, the children are learning language. Another way of asking this question is, does the child teach the caregivers how to scaffold the child, right? Are the caregivers altering their behavior in support of language acquisition? And as you can see in this plot, the answer seems to be yes, again, at least for this child. Okay, so this plot takes a little bit to digest, so let's, as usual, go through the horizontal axis and then the vertical axis. So on the horizontal axis, we have time again, but not 9 to 24 months. We have at the center here the moment at which the word was birthed by the child. Obviously, the child is going to utter words for the first time at different times during this 9 to 24 month period. We're going to take all of those times and shift them horizontally so they all line up at 0 here. So for all the this corresponds to various points in time, which is when the child issued a word for the first time. So if we move to the left here, for a given word, we can ask what was happening before, earlier in time, months before the child uttered that particular word for the first time. If water was emitted late, we can go backwards and look at when the caregivers uttered the word water. If another word like mama was issued earlier, we can again go even earlier and ask how often was the word mama mentioned by the caregivers. Okay. The vertical axis here represents change in mean length of utterance. So let's go back to 0 here and take a particular word, water. We can march backwards in time and find in the audio transcripts occurrences of the word water, and then look at the sentences in which the word water was embedded and count the number of words in that sentence. Do you want water? That's a length of utterance of 4. Want water? That's an utterance of length 2. So 4 plus 2 divided by 2 is 3. So if we found two sentences that contain the word water, the mean length of the utterance is 3. And we can then average the length of those utterances month by month. So at the moment that the child uttered the word water, during that month, what was the average length of the utterances that contained the word water? We're going to normalize, it might be 2. So around that time, maybe the caregivers were saying want water, want water, want water a lot. and then the child said water for the first time. A mean length utterance of length 2. So we're then going to march backward in time and ask, does the mean length of utterance, is it different from 2? And you'll notice that in this case, and for all of the words, most of the utterances that contained the word that was birthed at this time were longer than the utterances during the month at which the child birthed the word. So there's a lot of normalization and shifting here. Does this make sense? It does not mean that at the moment it does not mean that in the month that the child uttered the word for the first time that all the utterances were length 0. That doesn't really make sense, actually. It means that the sentences containing the word were longer, but months and months before that word was spoken for the first time, the caregivers were shortening the utterances or the sentences that contained that word. Might not be surprising that that happens, a few weeks or a few days before the child utters the word, because the child is uttering the child version of that word, gaga. So the child is giving probably hints to the caregivers that they're getting ready to say the adult version of that word, and that might trigger the parents to scaffold the acquisition of that word. They might start shortening the sentences that contain that utterance. One of the amazing things about this plot, at least from my point of view, is that this is occurring in some cases over a year before the child utters that word for the first time. You'll notice that after the child has uttered that word for the first time, the mean length of the utterances start to go up. What is that telling you? What's happening? What does that tell you about the behavior of the caregivers? At least it tells you that they're using longer sentences that contain that word. What does it suggest about the interaction between the parent and the child? The parents and the child. Remember, we're talking about scaffolding here. The drop in length of utterances is the addition of the scaffolding, right? The parents are making it easier for the child to utter that word for the first time. Water, gaga, water, gaga, water, gaga, water, water. After this period, as the length of the utterances are starting to get longer again, this is the parents removing the scaffolding. They're demonstrating, I should put this in the form of a question, this is a hypothesis. Are the parents helping the child master the use of this word? How to use this word in combination with other words, as Ethan was mentioning? Are the parents helping the child to form a core lexicon and how to combine words together in more complex ways? It's not immediately clear, but you can clearly see the addition of scaffolding and the removing of that scaffolding from the point of view of the parents. And when that scaffolding is added and when it's removed is predicted by the month in which the child utters that word for the first time. So it may be not so much that the parents are teaching the children language, it's that the children are teaching the caregivers. The children are teaching or signaling to the caregivers when to apply scaffolding and when to remove it. Kind of interesting. It has been known in linguistics for a long time, or developmental psychology, that the learning of language by a young child is not unidirectional. The child is not purely passive and taking in information. There is some give and take, but again, this data-driven approach to this question makes this interaction much more clear and suggests how this interaction is unfolding over time. Yeah, so the mean length of the utterance. So if I utter a whole bunch of sentences with the word water in it, what's the mean number of words in each of those sentences? Okay, that concludes lecture 19. Any questions about this particular study? Ubiquitous computing. Any questions before we move on to lecture 20, where we're going to start to introduce this third class of technology, robotics. Okay, so Why are we talking about robots in an HCI class? As I mentioned, part of the reason is because that's my home area of research, but robotics is a very important part of HCI in its own right, because a robot is an interactive technology. It takes information in from the world and produces actions, and those actions influence its environment, which influences the robot's relationship with its environment, which influences what it does next. A robot, like humans, pushes against the world and observes how the world pushes back. So as we discuss robots today and Thursday, I want you to keep the interaction of the robot with its environment at the front of your mind. This is the most important thing. The internals of the robot, how it transforms its sensory input into motion or output, is less important. What's more important is what's coming in from the outside world and the influence of the robot on its environment. If we have a robot that is turning towards a light source, for example, it's emitting some behavior, a person who is observing that robot is taking as input, the person is seeing the behavior of the robot, so the robot's behavior becomes input to the person. The person may be holding the flashlight, and based on what the person senses, they may come up with an idea about what the robot is doing and move the flashlight. What is the person doing? The person, as always, is creating a mental model of what they see. We spent a lot of time talking about this. One of the challenges historically in robotics, one of the reasons that the development of robots has lagged behind the development of computers and smartphones, is that our mental model of a robot, or our mental model of an animal, which is usually, and animals are usually our models for building robots, our mental models are wrong. If we observe a robot or an ant that is following a light source, we might imagine that that robot or that ant is getting an image of the world around it, recognizing a flashlight, or in the case of the ant, it's recognizing the sun in the sky, turning towards the sun, figuring out how to move, how to turn towards the light, and then moving towards the light. This is it may seem simple, but this is actually a relatively complicated explanation of what may or may not be going on in the mind of the ant. If we have an overly complex mental model of an animal, if our mental model of the animal is wrong, we might build that overly complicated mental model in the form of code into a robot, which is what this cartoon is trying to show down here. And we've programmed this robot with an overly complex controller or brain, and the robot doesn't work. This is sort of a 1-minute summary of what has sort of stymied robotics process for many decades. You might remember when we talked about Kismet and Jibo, the interactive robots. When we look at animals, we tend to anthropomorphize them, or we may attribute more complex behavior, or we may attribute overly complex cogitation, what's going on inside the head of the animal, than is actually there. That tendency to anthropomorphize animals means that we take those complex models and build them into our robots, and they don't work. Okay, so a lot of things we've already seen from HCI now, which raises a question in robotics, which is if we want to make robots that can interact with the environment, maybe we need to we need to program them more simply. We need to put less in there, and instead allow the robot to exploit its interaction with the world to learn about the world and get along in the world safely and efficiently. Okay. So in order to explore this idea of rethinking robotics, coming at it from a simpler point of view, I'm going to show you a series of hypothetical robots that are taken from a book by Valentino Breitenberg called Vehicles. Why is the book called Vehicles? Well, for most of us, vehicles connote an artificial machine, right? An autonomous car or something else. Breitenberg meant vehicles as a term that was meant to span animals and robots. So when we're talking about vehicles here, you can think about these as a hypothetical animal or a hypothetical robot. Why did Breitenberg write this book? Well, Valentino Breitenberg was a very accomplished neurophysiologist, meaning he studied the physiology or the anatomy of the brains of animals. He particularly focused on the fruit fly. Most of you probably live in student housing, so you're probably very familiar with fruit flies. If there's any rotting food over a couple of days, suddenly you get these very, very small flies, these fruit flies, which, as you probably know from firsthand experience, they're extremely good at detecting the odor of rotting food stuff and flying towards that food. How do they do that? There were many theories back in the 60s and 70s about how fruit flies do this, which is that they smell local odor gradients as they're flying. They perform differential calculus in their head and orient themselves toward the smell and head in that direction. Breitenberg, who actually studied the brains of fruit flies, you know how small a fruit fly is. You can imagine how small the brain of a fruit fly was. Breitenberg was pretty sure that all these theories about what was going on in the head of the fruit fly were overly complicated. There was no way that a brain this size was performing complex calculations about detecting gradients and then computing change in heading based on that gradient to head towards the rotting piece of fruit. So Breitenberg started doodling with other hypotheses, other ways in which a self-moving animal, or ultimately a robot, might be able to detect signals in the environment and be able to exploit its interaction with the world, rather than rely on internal complexity to find the rotting fruit, move towards the light, and so on. These doodles eventually became a book, again called Vehicles. It's an interesting book. It's not very long, less than 100 pages, and it's written like a fairy tale, broken up into chapters. In chapter 1, Breitenberg introduces Vehicle 1, which is about as simple as you can get. Vehicle 1 has a body. We're looking at this vehicle from above. It has a body. It has a single wheel. Has a single sensor on the front, and in Vehicle 1 we're going to assume this sensor detects temperature. The higher the temperature, the more strongly this sensor fires. The lower the temperature, the less frequently or less strongly this sensor fires. Imagine that this single sensor is attached by a single wire to the wheel. If you take this very simple vehicle and put it, for example, in a pond, Breitenberg said, imagine what you would think if you saw such a vehicle swimming around in a pond. You might say it's restless and does not like warm water. Why does it not like warm water? Because if it's in warm water, the temperature sensor is firing strongly, which causes the wheel to turn quickly and the vehicle moves quickly through the warm water. The moment it hits a cold spot, a colder patch of water, the sensor fires less strongly, which means the wheel turns more slowly, which means the vehicle moves slower through cold water. So it's restless, you might say. It doesn't like warm water, but it is quite stupid since it's not able to turn back around to the nice cold spot that it overshot in its restlessness. So this vehicle will move slowly through cold water, but eventually leave that patch and enter an area of warm water again. Anyway, you would probably say that this is alive since you have never seen a particle of dead matter move around quite like that. Okay, so what Breitenberg is inviting us to do is to imagine we're seeing just the behavior of this. We're just watching the behavior of this creature. Assume we don't know what's going on inside that creature. As he points out here, if we don't know what's going on inside, we might start to anthropomorphize already. It's restless. It doesn't like. It's stupid. It can't turn around. You remember our discussion about HAL? Maybe a vehicle is upset that it can't turn around. Maybe it regrets the fact that it's now no longer in that nice cold patch that it enjoyed a few seconds ago. Okay. as Bradenberg is pointing out here, we might overshoot what's actually going on inside this creature, which we know is simply a single sensor attached to a single motor by a single wire. That's vehicle 1. Okay. In chapter 2 of vehicles, Bradenberg introduces 2 different vehicles, vehicle 2A and 2B. Let's start with vehicle 2A. Slightly more complicated than vehicle 1. We have 2 sensors on the front of the vehicle, 2 wheels on the back. We're going to assume now that these 2 sensors are light sensors. You'll notice that there's a little plus sign next to each of the 2 wires, which represents a positive connection. So the stronger the sensor fires, the faster the wheel turns. If we came at this robot with a flashlight turned on from the robot's front right, so if the robot detected a light source in front and to the right of it, how would this robot move? Now we're assuming, obviously, we can see inside the robot. If this robot detected light to the front and right of it, how would this robot move in the next time instance? If you have an idea, go ahead and type it into chat. Would this robot go forward, turn right, turn left, stay still? As Thomas says, this robot would turn left. Why would it turn left? What's happening here? Can we dig down into the sensors and motors a little bit? If you think about it, the two light sensors at this point in time, there is more light falling on the right sensor than there is on the left sensor, because the right sensor is closer to the light. Since the right sensor is more activated than the left sensor, the right wheel is going to be turning faster than the left wheel, which means the robot turns to the left. Remember that a robot is very different from all the other technologies we've seen so far, because like us, like animals and humans, the robot is self-motile. It can move itself. The moment it moves itself, it alters its interaction with the environment, or it alters its relationship with the environment, which means through its own actions, it's going to alter its sensory perceptions at the next time step. So imagine this robot does move a little bit forward and to the left. What does the robot do at the next time instant? After it's moved forward and a little bit to the left, what's it going to do next? The values arriving, or the amount of light arriving at the 2 light sensors is going to be different the moment it moves 1 centimeter up and maybe 1 centimeter to the left. What's going to happen next? Let's imagine that this robot moves forward and to the left enough so that now the light is here and the 2 light sensors are here. So they're sort of parallel with the direction of the flashlight. What does the robot do at that point? What can you tell me about the 2 sensors? The moment this particular robot moves a little bit up and a little bit to the left. How are the values at the light sensors now different from the values of the light sensors just previously? Does it keep moving in the same direction? One light sensor will be even more activated. So if you think about, at this point in time, think about the difference in light values falling on the sensors here. If these 2 sensors are now here, so that they're parallel, closer to and parallel with the flashlight, there's going to be way more light falling on the right light sensor than there was before. And the difference between those two light sensors may be even more. It's going to turn more to the left. Yeah. Okay. I want you as homework to think this through. As this robot continues moving, how does it continue moving? And we will start up here on Thursday. You have a quiz due tonight. And you're working on deliverable 10. I wish you a good rest of your day and see you all on Thursday. Thanks very much.